Got a selection of multiple choice questions here on the equilibria topic. They're all past paper from AQA Chemistry. I'm going to recommend you pause on each question, try it before you see the solution. Here's the first one. And on here, we're going to use the principles that underpin Kc calculations. We need to know how many moles are at equilibrium. So I'm going to start by drawing out my table, initial moles, equilibrium moles. I have my three species there. I'm told I start with 1 mole of ammonia. I can make an assumption. I started with 0 moles of product. I've also been told that I've got a 50% dissociation. So half of my ammonia has broken down. That means that I've got 0.5 moles left. If I then take that a step further forward, I can look at my mole ratios. 1 mole of ammonia makes half a mole of N2. I've used half a mole. That means that I'm going to make 0.25 moles of N2. And similarly, I can look at my mole ratio of NH3 to H2, which is 1 to 1.5. So my 0.5 would make 0.75 moles. What I then now have are my 3 moles of gases. I can add those together, comes to 1.5. Correct answer is A. On to the next question, and we have got here a bit of Le Chatelier. And now you've had a go to try it, let's work through. Going to dismiss D straight away because catalysts do not change position of equilibrium, they change how quickly equilibrium is reached. If I then go on to pressure, if I lower the pressure, actually I've got more moles on the left hand side. Lowering pressure will shift equilibrium to the left, that will mean less SO3. Now let's move up to temperature. This is an exothermic reaction going forward. Raising the temperature would actually favour the endothermic reaction. It would shift the equilibrium to the left, giving us less SO3. But finally, if I've got O2 and I add more O2, the system's going to try to remove it. Equilibrium shifts to the right, we get more SO3. Correct answer is A. Have a go at this one now. So on here, you've got to be careful that we're looking for the answer that is not correct. Let's go through them. Well, the first one, that is correct. It's done using concentrated phosphoric acid, which is a fact you need to remember from the alcohols topic. The higher the pressure, the higher the equilibrium yield of ethanol. Well, 2 moles makes 1 mole. Increasing pressure will shift equilibrium to the right, which will give us more ethanol. That's correct and therefore not the right answer. If I go on to look at part C, the forward reaction is exothermic. The higher the temperature, the lower the equilibrium yield, because raising temperature would favour the endothermic reaction. And if we take a look at the last one, we wouldn't say it's acceptable because the unreacted ethene is recycled. We would aim to get the maximum possible yield. So the correct answer here is C. Next question for you. And on this one, we have got, again, a range of statements. So let's have a look at them. I've got 1 mole on the left and 2 moles on the right. Now that means that if I increase the pressure, the equilibrium is going to shift to the left. It's going to give us more COCl2. Not decrease, as the question suggests. If we move on to part B, using a catalyst does not change position of equilibrium, it changes how quickly you get there. If I move to part C, reducing equilibrium constant will increase the value of the equilibrium constant. Reducing equilibrium concentration will increase the value of the equilibrium constant. This is dependent on you remembering that Kc is temperature dependent only. Kc is fixed for a specific reaction at a specific temperature. That means C can't be correct. So we get to D, and let's write out the expression. And increase favours endothermic, we know that. That does mean that there will be more product. Now, if we take a look at what that does to the Kc value, my product value goes up, my reactant value goes down, and that does mean that the Kc value would go higher. Quite a complex question there, one that's definitely worth revisiting. Okay, next question to try. So I'm going to start by writing the expression because you are going to have to do a calculation. But once again, you're going to need to work out equilibrium moles. So I've got my table drawn out. I have my initial moles, my equilibrium moles, and my initial have been provided. 4.2 of CO, 2 of steam, and I can make the assumption I started with 0 moles of product. Now I've also been told I've ended up with 1.6 moles of hydrogen. I'm now going to use my mole ratios to work out the rest. For every mole of H2 that I make 1 mole of CO2. If I made 1.6, I made 1.6. I also know, actually because this is a 1 to 1 to 1 to 1 ratio, to make 1.6 moles of CO2, I've used 1.6 moles of CO, so it's gone down to 2.6. To make 1.6 moles of CO2, I've used 1.6 moles of H2O. That gives me 0.4. I've now got my values to put in. You might notice these are number of moles, they're not concentrations, but because the volumes all cancel out, that doesn't matter. I can do this directly with the number of molecules. And that will always actually be true for anything where the Kc has no units. The V will cancel out. I do all of those, I get to my answer 2.46. The correct answer is D. That takes us to the end of this video. Thank you for listening and goodbye.